Greetings, everyone, and welcome to this latest explainer on strength of materials. And today we'll be covering Hooke's law and finding out why everything is a spring. So far, we've talked about parts being under load, and that can be either compressive or tensile. And just about everything with small deflections, just about every part you run into is going to return to its shape, just like a spring. So, I mean, the springs that you're seeing here, they can do a wide deflection, but even small things like, I don't care, cardboard or whatever, they will return to their shape just like a spring. Okay, so that includes even very strong materials like concrete, steel, wood. Um, they still will follow Hooke's law. Uh, he worked on a lot of springs. And one of the reasons why is that they were trying to figure out how to navigate in the middle 1600s, how to navigate the oceans without knowing longitude. They needed to keep accurate time, and they couldn't bring a whole big grandfather clock, or for that matter, a water dripping type thing on a ship that was moving to and fro and back and forth. They needed something accurate and very, very portable. So Hooke was saying, oh yeah, we can make these things with these really strong, these wound up springs that will help keep time, like a watch, a spring watch. And they didn't have, a lot of developed technology to make really, consistent springs and stuff like that. And so he was working on that. So he was looking at how to make springs and how they were affected by their size and the materials and all that stuff. And so he developed this thing, about a spring constant here. So the force here is equal to K, which is a spring constant of that part times X, which is some deflection, some movement of it. So the force is proportional to the deflection. That's one of the most important things here. So we rearrange it so that this K, this constant, is equal to force divided by the deflection. Now that was great for individual parts. Problem was that if you had a new part, you had to do all sorts of new testing to figure out what this was every single time. So what developed after that was Thomas Young, very bright person. He generalized Hooke's concept to the material itself. So if you knew the geometry of the material, you could figure out how it's going to deflect, what shape it's going to take, what stretching and all that kind of stuff, without doing testing on that particular part. It didn't matter what size the part was because it's made of this material. He says, hey, this is a material property. So what he developed was a similar thing. So in this case, E, instead of the spring constant, we have this elastic modulus is equal to the stress divided by the strain. I know we've already talked about stress. So this is the axial stress, which is force divided by area. Notice that for the spring, we had force in here too, but in this case, we're dividing it by the area. So that's 2 dimensions that we are normalizing it for any particular part. And so that's the area, force divided by area. We're using stress. And here's the strain. The strain is the change in length divided by the original length, taking care of that 3rd dimension. So between the area and the length, we normalize this thing for any part. So Young took the same concept, applied it to materials in general, and now we can use this as a material property. We don't have to worry about whether the area or the length are going to change the behavior. We know where they are, but we can account for it very easily just by calculations. So the strain thing here, it's really, really important. It's like the 2nd most important thing compared to stress, but we're putting them together here in this elastic modulus concept, and we're going to put them together and do some really neat things with it. So showing you this tensile test specimen. So if we have a length here, like this. Okay, and then we stretch this out and we move this some, like, say this is 2 inches, and we move this and it moves 0.01 inch, then our strain is equal to 0.01 inches. So that's the delta, the lowercase delta. Okay, and our original length is 2 inches. So 2 inches. So our strain is 0.01 divided by 2 is 0.005. Units are inches per inch. And of course, those cancel out, right? So you could actually leave them in there. Sometimes people actually use them inches per inch, but we can also translate it into a percentage. So those cancel out, and we translate it into 0.5%. So this specimen here would have stretched by 0.5%. All right, that's very common usage of the strain. All right, so remember that E, the elastic modulus, is a material property, has nothing to do with the size, geometry, or loading conditions of the material. So it's really a nice step forward in how they develop new materials, new designs, and stuff like that. However, there's a major limitation. It's only applicable within small ranges. Metals might have some larger ranges with they call the elastic range, but many materials have this is only good within a very short range of deflections. Depending, it might be a few percent, it might be 10 or 20%, but it's only applicable in small range. But often it's very, very helpful even within that limitation. Okay, so you see here, if you get to this point here with necking, yeah, things get a lot more complicated. All right. Okay, so what about deflection? This is something that's really important for us to know. So if you've got a bridge that you want to make sure it doesn't bend so much under the weight of a large truck, then you want to know its deflection. Well, according to these formulas that we can use, not so bad. We need to look up first is that elastic modulus, and we can look that up in tables. So here is a table from your book, or there's a lot of other places to look online, and you'll see right here, modulus of the elasticity. Now you got to make sure you look at the units here, PSI or gigapascals. So this is just an example. You got stainless steels, copper, magnesium, and make sure you use the proper units. Often up here, you'll see PSI times 10 to the 6th, and then you'll just see 28 or 29, whatever. So watch out to make sure you use the right units. This is gigapascals. That's 1 billion pascals, or I like to think of them as 1,000 megapascals. Okay, so we can rearrange those formulas that we just went through to figure out the different variables. So that's how we're going to find the deflection. And deflection is really easy and important to work with. To find the deflection, we're going to start with the definition of the elastic modulus. And rearranging it, it's actually very common to show it like this, where stress equals the elastic modulus times the strain. Okay, by the way, this is the Greek letter epsilon. Okay, and we use that for strain. Now remember, stress is also, right back at the beginning of the year, force divided by area. So we now have the elastic modulus times the strain equals force over area. So we can use this. If you remember that strain is the deflection divided by the original length, and we're going to take this and plug it into here and use the elastic modulus times deflection over length equals force over area. And I'm going to multiply both sides by what I want to get rid of over here. So I want to get rid of E and L because I want to get make this all by itself. So I'm going to multiply this times L over E, multiply this times L over E, and these will cancel out, and these will cancel out. So I am left with deflection equals PL over AE, and that is my formula. And it's worthy to say also within the elastic range. Okay, so it's again a limited situation, but very, very useful because often we are designing within these limited situations. So there we have it. Delta equals PL over AE. And so if you ever ask, what do I use? I'll say, oh, let's go out and play. And so this is my way of reminding you, deflection equals play, PL over AE. All right, so let's do another quick example of solving for stress. So we're going to rearrange the formula using algebra. So let's say we're given that we've got titanium. This is one of my favorite materials, titanium alloy Ti6Al4V. So we've got some aluminum and vanadium in there. And we have a sample that is 15 centimeters long. All right. And we just know we've done a test on this, and we deflected it 0.02 millimeters. So we know what our material is, we know what our length is, we know what our deflection is. That means we should be able to figure something out here, and that is we're going to find how much stress we put on the sample. First thing we're going to need to do, though, is we're going to need to look up the values that we need. So I'm going to go over here to our textbook values, and this is the one I was just showing you before, but if I scroll down a little bit, I've got titanium and its alloys, and I've got Ti6Al4V right here, and I'm going to look it up, and I've got 16.5 times 10 to the 6th what? PSI, okay, and 114 gigapascals. But because I'm using millimeters and centimeters, so I think I'm going to want to use the gigapascal one. All right, so that was 114 gigapascals right here. And so I'm going to do lookup. And E, the titanium, is 114 gigapascals. All right, and I'm going to translate that right off the bat because we need to watch the units all the time, to 114,000 megapascals. Also, while I'm at it, I'm going to make this not 15 centimeters long, but 150 millimeters long. Okay, so now I'm going to use our play equation. Delta equals PL over AE. Problem is that I don't see stress here. I'm looking for stress, but you do see stress. You should see stress. P and A together make stress. So I'm going to solve for P over A. I'm going to multiply both sides by E over L because I'm trying to get P over A by itself. Okay. And so I'm going to rearrange this, cancel these out, E, E, L, L. All right, so I'm going to rearrange it. So P over A is here. P over A equals delta times E over L. All right, and we've got our delta up here of 0.02 millimeters and times 114,000 megapascals, and all of that over L, which is 150 millimeters. Okay, so let's look at the units on that. going to cancel out the millimeters with the millimeters, and then everything else should just be easily calculated. So I've got 0.02 times 114,000 divided by 150, and I get 15.2 watts. Okay, well, everything else canceled out other than megapascals. So I've got 15.2 megapascals, and that's it. So we found out the stress on our sample here just using the length and the deflection and the fact that we knew that it's titanium alloy. So it was we did not need to know the actual force or the area. We didn't need to know anything about that part of the problem. Okay, that was kind of cool. But make sure again that you watch the units. Now there are a bunch of other examples that I have in the playlist. And so hopefully now you'll be able to watch them and understand them a little bit better as to what I did and why, most importantly, why there. Okay, so in summary, remember that all materials are springs within certain short ranges. Okay, you can't, just keep going and expect it to be linear, but they have these linear characteristics when they are loaded over a short distance. And you can use that equation right there to find the force if you've got the other ones, find the area if you got the other ones, whatever it is. And you can look up, if you know the material, the elastic modulus, all those kinds of things. And you'll have to rearrange this equation, but it's very powerful in that that's what can be done with it. And so this is one of the most important equations. Make sure you tattoo it backward on your forehead so you can remember it every time you look in the mirror. So rearranging that formula is very important, being able to do that. But also you have to be careful with the units because you might mix up centimeters, millimeters, inches, feet, whatever it is, pounds, tons, kips, all those things. You have to know how to do those in order to manipulate this and solve the problem successfully. Okay, well, I hope this helped, and thanks for watching. And let me know if there's anything that really helped you or anything that could help you even more. Thanks a lot.